Okay, let's begin. So we're back with Statistics 5114, if you're in the text. If you're viewing virtually, it's good to see y'all, or not. So it's good to see everybody in the room. I'm pretty motivated these days to get on campus, get my day started. So thanks for joining me in that. It's a lot more fun seeing you guys here. I want to go through the Bootstrap today. I want to talk about several aspects, but mostly I'm going to demonstrate it to you. You're going to ask me a lot of mathematical questions. How many Bootstrap iterations? How big does n need to be for the Bootstrap to work? My answer is going to be, do you guys know? It depends. So if the function, if what we're trying to estimate from comes from a function that's super wiggly, and it has a lot of variation in weird ways, we need to see more data so we can understand how wiggly the function is. So wigglier functions need more data. They need more data where things are wiggling. If you want to estimate things in the region where everything's wiggling. So again, it depends. So I know you guys would like a rule like n has to be 30 and then everything's good. Well, I'm going to tease you a little bit. I'm going to say my n has to be 31 just to be a little bit better. So again, those are bad rules of thumb. You need to check to see how well it works. So what I always recommend people do is build simulation studies that look like your problems. So, or problems that are kind of akin or complicated in the way that your real problems are. And so the reality is we don't know until we demonstrate everything. Our theorems are usually limiting. They say something like, if n goes to infinity, then we do really well. And I'm going to suggest that's true of all decent methods. So, saying that, we never get to see n at infinity because it's not a real thing. It's a concept. So asymptotically, everything depends, and it depends on the problem at hand. So I think in this class we need to do math and demo things, compare things explicitly, and then understand the underlying theory. So if we can put both of those things together, we'll understand our problems. We'll know our limitations as well. Okay, I want to start off with this conversation, and we're going to come back around to it. In the context of hypothesis testing, we were talking last time and the time before, and I was saying something like fx given theta is a conditional probability, and I was saying that. So, and that's how I think about these things. That's not everybody. Some people say in the frequentist paradigm, this is not what they believe. And again, it depends on what kind of frequentist you are. So whether or not you're willing to accept this thing as a conditional probability, theta to you might be fixed, but that could still be a random variable to you. And so you're just really sure about where it lives. I find these arguments to be nonsensical and just the sort of thing that people do just because they like to argue. And in academia, we do that. So we love arguing. Does anybody know who Mayo is here? I could blow this up a little bit. This a little bit bigger. Does anybody know who Mayo is? Where she's from? She lives in Blacksburg. So she's a faculty, or at least she's an alumnus of her Department of Philosophy. She studies the philosophy of statistics. So I say, cool, because that is what philosophy is, really. So if we think about philosophy from kind of its roots perspective, it's really just science. So it's, and then there's these questions, what's the best way to do science? And if you read through Plato or Socrates, Aristotle, they do believe different things, they're wrong. So they're great thinkers. They're wrong all the time. Saying that, they have interesting perspectives and sometimes they're close to being right. And so philosophy moves onwards. So I guess it's deep thinking about stuff. You know, it's pretty vague. If you're doing the philosophy of science, what's the best way to do science? I think we understand that it's all about the data that we collect. And so the philosophy of science is really the philosophy of statistics. So I congratulate my colleague for being a philosopher of the thing that's most important in science, that is stats. Saying that, I'm a practicing statistician. I do have a PhD, so that means I'm a doctor of philosophy, all very general stuff, and you guys will be too. Many of you will be in this room. It doesn't mean we know things, it means that we study things. So, and we continue to study things. Okay, so I practice statistics. A lot of my stuff is applied based. When I come up with theory or methodology, it's usually in the context of a real problem. And so I like to see what works, what doesn't work. Then I pontificate. At the end of the day, I write some code and I prove some stuff. But I really demonstrate how well methods work. And I think everything is about the demonstration. Now, I understand in math class, they don't like pictures and they don't like demos. It's all the theory, and that's all that matters. So I'm a little bit broader. All the things matter. Things that matter, you can put them together, and they matter even more. Okay, we were talking about interpreting this as a conditional probability. They're going to have this discussion in the context of p-values. So if you know what a p-value is, it's the probability of data that's more extreme. You have to define what that means, given your null hypothesis. A lot of people interpret that statement as a probabilistic statement that's conditioning on the hypothesis. I certainly think about it that way myself. It's really a question of what are we going to do once we think about it that way. It doesn't force you into being a Bayesian, but it forces you into thinking about things in terms of random variables. For me, that's not a big stretch. We made all this stuff up anyway. So this was not delivered to us by the hands of the statistical gods. Rather, this is man's work of trying to understand what's happening in reality, testing things and setting up paradigms that people can come back and falsify the claims. That's what science is. It's the opportunity to falsify what somebody's saying. That's what makes things a hypothesis. I do agree with some of the authors in this, and I disagree with some of the authors. We're all going to have our opinions, and that's okay. So you're allowed to think about this however you want. So instead of talking about theta per se, they're going to be fixing something conditional on some pre-specified theta, and that's going to be our hypothesis. So really, even in the context of hypothesis testing, they're usually fixing theta to be something. So I will interpret that as a conditional probability. Maya, however, will not interpret it that way. So she says, one of the main sources of confusion about p-values is the supposition that it is a conditional probability in the first place. And because she feels strongly, she says, I am not. It is not. So she feels very strongly. She lets you know that by putting an exclamation point. So adamant. So I kind of like these techniques. So when I say it's this, period, I probably should start saying it is this exclamation point to let you know I'm even more serious about it. And the louder I get and the angrier I sound, the more I believe it. So we don't have to do that. That's a choice we make. So she interprets this quantity differently. Her conditioning is different from the way I think about conditioning. I think about it probabilistically. So she continues. You can read through all of this if you would like. You can even find the blog that this came in. So if you take a couple sentences, type it into Google, paste it in there, you will find the blog that this goes in. So a lot of statisticians and scientists have blogs, so I do not. But you can have one if you want, and you can discuss your opinion, and you can get people riled up if you want. It'll work. So she says she thinks she knows what happens here, why we're all confused, people like me, why I'm confused. So she says, what I think happens next involves an informal use of the word probability in English, which is not akin to formal Bayesian computation. I have a real problem with that statement. There's a big hook in there. How did we get to Bayesian computation from this argument? So she's having arguments with Bayesians. I'm not sure that that's the right verbiage, but that's how I always think about stuff when I read Professor Mayo's work. I'm always confused by her language because she uses a different language than I use. And so usually we're just arguing about semantics. And then there's some cookie cutter problems that we play ping pong on and see who's going to win the game. We've done this before. I welcome it. It's not my favorite activity. So is to just quibble over semantics. So instead of just writing down, here's what I believe and here's how well it works, and here's my theoretical basis for believing what I believe, and more importantly, I have my demonstrations that what I believe can lead to good things. Let's keep in mind that probability distribution, probability is something that we created, I think. So I think people have created this construct. I'm not sure that this is a natural construct in reality. I'm not sure how the universe works, but I think this stuff we've made because it works for us. It's a tool. Some people would like to claim that it's a little bit more divine than that. That this is reality. I wish I could believe that. That would make me feel really good about myself, but I don't. So that's just my opinion. She continues after bringing up Bayesian computation, where I'm not sure exactly where that fits in. I think it might be a slur by saying we don't understand theory, we're just computationalists and doing things. I guess that's okay. So I feel more strongly than that, but I guess that's okay. One may say of a claim that is passed with high severity, or one that is highly corroborated, that it's probably true. So she's mincing the technical definition of probability and what we say in English, that we're saying probably true, therefore I mean conditional probability. The Bayesians jump up and down and rejoice. I've never done that, so it's never happened. This is just to strike the point that there's different people, they're very bright, and they disagree with each other. And if you want to see more examples of that, just read history. You can read it in any field, and unfortunately, people do disagree. That's what science is about. And then demonstrating to people maybe the utility of their arguments. I think that's the best we can ever do. Ed George comes in. Ed George is a professor at University of Pennsylvania. I think 2 years ago he was here giving a talk, so he's a friend of the department. He goes on to say, this function right here, this is a p-value, conditional on the hypothesis. He writes it down like this, using the conditioning bar in exactly the same way I use it. He says, how is this thing, this probability distribution of more extreme data conditioned on something, how is that not a conditional probability? He says it is. So, he goes on. Mayo comes in and says, you write this is Andrew Gelman here that's coming in, and he's going to agree with Ed George. And he says the p-value is a conditional probability. So these statements, conditional on some fixed theta, that is a conditional probability. So he says it is. Mayo still says it's not. Let's see if anybody convinces each other. Mayo comes in, no, it's not. So it's like preschool. It is, it's not. It is, it's not. So again, if you want to think about it as one, I guess it is. If you want to think about it as something else, and it's not the way I think about it, I guess that's how you think about it. So it's more of a question of what are you going to do once you think about something. And I think that's where the real debate is. They don't want us to do certain things. You interpret it that way, you can't interpret it, so it makes your whole paradigm void. I don't believe that. So Gelman says, well, let's just finish Mayo's comment. No, it's not. The required joint and prior are absent. So she's using Bayesian language. So again, knowing who she's arguing with, they're probably Bayesians. So they take this thing and they apply Bayes' theorem to it to flip the conditional statement. So to invert the problem. We'll be talking about that in a couple weeks, in about a week or so, maybe a week and a half. First, we're going to study a few other paradigms, and then we're going to jump right into Bayes so that we have at least some frequentist tools, some computational tools, some asymptotic tools, and some Bayesian tools so that we have context. Okay, so she says the required joint distribution, it requires a joint distribution. So if you want to interpret this as a conditional distribution, you have to write down first the joint distribution of x and theta, the data and your parameters. So she's in a very simplified way saying that you haven't defined the sigma algebra on theta. So I usually just say to people, let's assume that we did. So, and it's done. She's going to say the problem didn't come at you like that. It came at you like this. But it didn't come at us like this. This is something we write down. What we usually see is data from our distributions. So we don't see the function in the first place. Everything comes at us like data. So some points in there. If I were to IID sample from this distribution, I'd just be sampling points, and most of the points would live in the mass of the distribution. I'd have more points here because this is higher. So these would probably be a bit denser than these. And at the end of the day, I could draw a histogram representation of this function. So I could start to learn what this function might look like by observing some data. So if we're able to presuppose this, I can presuppose anything mathematically that I want. So again, that's something that we usually have to create. Now in this class, I get to give it to you. So that's the fiction in my classes. I tell you what F is. In reality, we have to build that as well. It's all part of our process. So if we're going to build that, I think that we can talk about things jointly. Deborah doesn't feel that way. So I'm going to suspect, since she can read my mind, that the reason she thinks this is because she doesn't work with data. So, touche. Andrew comes in. Oh, let's finish this up. No, it's not the required joint and prior accent. That is why people like myself and David Friedman, this is a classy technique as well, is invoke another person. This other person said something. So I'm citing them. She doesn't need to, but she's telling us who her friends are. So Friedman is a well-respected statistician and probabilist. So I think what you should do when you're reading through these things is just get a sense of who these people are, what they do, and you'll have a better understanding of why they believe what they believe. That's what I do. But she says people like David Friedman introduced the double bar. So can't send a reference now, traveling, but David Friedman does do that. And instead of writing this bar right here when he conditions on his null hypothesis, he puts a double bar to tell you it's not exactly a formal conditional probability, but we are conditioning on something, but not in the probabilistic sense. And I guess the double bar is a shield against creating defining theta as a random variable. I'm not sure I get it, but that's fine. Andrew comes in and he says, well, I don't see the need to introduce new notation, given that the existing notation is unambiguous. Clearly it's ambiguous. So why else are they having this argument? But for him it's unambiguous, and for me, in an operating sense, it's totally unambiguous. From a what is true sense, what is the actual reality, the state of the universe, I don't think we'll ever know that. So I'm not positive that this defines the state of the universe. Again, we write this stuff down because it's useful. It's a tool. That's what I do. So, and George comes in and he says, I look forward to seeing which new notation overlap statisticians will have to cope with in the future. So he's not looking forward to it. So, but we love to create new notations to explain things that weren't well explained in the first place, or maybe they were super obvious and we didn't need to explain them in the first place. It's one or the other. So I think it's super simple. Some other people think otherwise. Andy comes back in and says, and of course, I don't think it's appropriate to have notation for intervention, so there's an argument that ensues in here, and he further expounds his point. Other people jump in. Andy gets accused of disagreeing with Judea Pearl, so some of you might understand what he's saying, but he's really working with causality and discussing causality. So I kind of like Andy's response. He's like, I don't think I have a disagreement with the guy. We just work on different problems. And I think that that's an important thing. It's which problems you work on, and that usually has a lot to do with why you believe what you believe. But the world is bigger than the 100 or so problems that you're going to work on in your lifetime. So you might work on 100 or 200 very difficult problems. You'll get publications for each one of those. But I like to look at what people work on. It's important. So they argue back and forth a little bit more. Bill Jeffries jumps in. He was at the University of Austin for, I think, the bulk of his career. Now he's retired and he lives in New Zealand. So nice choice. Want to get away from it all. But doesn't mean you don't have a little bit of time for some blogging. This is a little bit old. It's 2013. This argument still persists. And nobody's going to solve it for anybody. You can already tell by the blathering that nobody's convincing anybody of anything. So they're playing for the spectators. They're playing for us. And we get to decide who we cheer for. So this is almost like academic sport. Bill Jeffries comes in and comments on Mayo's comment, conditional probability is, and then makes his own statement. Conditional probability is just conditional probability. No joint or prior are needed. This is basic probability theory. I'm not sure I agree with Bill on that. So I think if you are going to talk about it in terms of a random variable, you are implying joint distribution. So, my opinion. So I agree with Deborah on her point. I just say that it's super easy to do. So I can presuppose it. If I can presuppose everything else I presuppose. So what Mayo means is this rule. So the joint divided by the margin is the conditional probability. So, and you can't talk about that until you've defined what the margin on B is, and you can't talk about it until you've defined the joint. So I agree with it. That is what you're doing, but in all these problems, we're setting up the mathematical statement and invoking whatever we want. And if it's useful, we'll probably continue to do it. So Conrad just comes in and makes it clear to all of us that we make sure we know what we're talking about. I think that's okay. Larry Wasserman, he's at Carnegie Mellon University. So he's kind of an interesting case. He's the, once upon a time was a Bayesian, and now is not. So there aren't a lot of examples of that. Usually you see it go the other way. So I was a non-Bayesian in my training because I was trained by classicists, meaning they're old, and then I figured out MCMC is really cool. The computation that Bayesians do are cool. Maybe I'll start adopting some of their mindsets as well, so that it at least makes sense to us. But Wasserman, he has his own blog, and he likes to argue as well. So his blog is interesting. Some of his points I agree with. Interestingly, when you talk to these people, the conversation is quite a bit different. It's not quite as jagged as all of this. And I do find that people can agree. Usually they just get tired. So that's how I feel. So Wasserman comes in, supports Deborah Mayo's statement, there is no conditioning. For conditioning, you need to condition on something random. From a frequentist perspective, H0 is fixed, not random. I don't agree with that statement. So why is it that the frequentist perspective is that? It could be any perspective. So I would agree most people that call themselves frequentists that might not know what it is and they poorly define what type of frequentist they are, they will usually use this argument. So this gets even cuter. So Bill Jeffries comes in and clarifies for us that we understand technically what's going on. Random variable is still a random variable even if its value is certain. So what he's saying is that it's a mathematical concept, a random variable. So it doesn't mean it's random in nature. It just means that you can invert and get back to the original elements, i.e. the data points x, and assign probability values to them, or density values. So if you can do that, you're working with a random variable. So it's that inversion that I can get to. So as an example of that, think about maybe rolling 2 dice, and I know what the probabilities are on those dice, and I sum together the faces of the die. And I want to know what the probability of certain sums coming up. To answer the question, I have to go back to the probabilities of the original faces of the dice. And if I can do that, and I can map back, and you can, so if I ask the question, what's the probability of observing a 7, it has something to do with what's the probability of a 1 and a 6, or a 6 and a 1, and a 2 and a 5, and a 5 and a 2, and a 4 and a 3, and a 3 and a 4, so on and so forth. And if I can answer what the probability of those things are, then I can answer the question, what's the probability of the transform, the sum of them. So if you can dig back and get back to those probabilities when your problem is set up right, that's a random variable. So that's a technical thing. In measure theory class, they'll go through this with you, but they're going to show you that it's an inverse mapping. That exists, and it's a random variable. Again, this is something we construct. I don't think that this was handed to us by the statistical gods themselves. They're busy doing other things. They don't hand us this stuff. They're willing to give us data, though. So a random variable is still random, even if its value is certain or fixed. So from a Bayesian perspective, if you said theta was actually random in nature, I'll do the exact same thing I would do if you told me theta is fixed in nature. So really all I'm going to explain to you is either how theta moves and what its variability looks like, or I'm going to be explaining to you that I'm uncertain about that fixed value of theta. And I'm going to use a random variable to describe that to you, how uncertain I am. That's what Bill is saying here. So random variable is a math thing. Arispanos. So one of Deborah's allies, they've written a book together, so you can't take this is independent information. They're colluding in the first place. So I kind of see this as, again, Deborah's opinion. Does anybody know where Eris is? He lives in Blacksburg as well, so he's in the Department of Economics. So, and he writes on the philosophy of statistics. He'll often come to our seminars and tell us that we can't do the things that we're doing. And usually to that I really reply, I'm going to do it anyway. So, Arispanos, I am amazed that competent statisticians are even debating this point. I'm amazed too, so just from the other side. Milo and Wasserman are absolutely and unequivocally correct. So good thing he said unequivocally. So otherwise I wouldn't know that he's absolute about this. So this is even stronger than an exclamation point. So he's really serious. So, and he's taking a jab. You guys are smart people, how can you believe this? You know, we do that all the time. So if you agree you're smart, then you will agree with me. So does anybody agree that they're smart? Who's smart in here? Oh, well then you don't need to agree with me. So again, I'm teasing. So I think we're all very confident we can come up with our own ideas and we'll have our own opinion on this. So unequivocally correct. Okay. So I like this last comment. Eris, you write of correctness and legitimacy and conclude with a period! Exclamation point. I really like that. So, humorous. So if you guys were able to watch his discussion the other week in the Stats Colloquium series, you'll kind of understand his personality. So he's witty. He's wittier than he seems. So a lot of the stuff he's saying is in a joking manner. All I can say is that I'm glad that people such as yourself aren't in a position of telling people such as myself what can and can't be done. I kind of like that. And then there's some other stuff in here if you want to. So the conversation goes on. Somebody got a little bit upset in the conversation and thought, we'd better LaTeX this thing up. So maybe that will solve the debate. It does not get solved. So at the end, we all disagree with each other. So I don't care what you think. I care what I think, and I don't even think it's necessarily correct. So I guess I should remove that statement, I don't care what you think. I kind of care. So I like to talk about it, but not until I'm blue in the face. So let's get some problems solved. So, or else we can discuss this forever. I do think about this in conditional probability. If you do not, that's okay with me. So my point about independence and exchangeability still holds. If you don't know theta, the x's are informing you about future x's by estimating theta. So through theta. So it's not a physical dependence. There's no like electromagnetic field that you see some x and it like all of a sudden does something and perturbs future x's. It's just that you can learn theta so you can learn future x's. So I've got this argument in my function that I'm going to move around. I think of it as a random variable. Other people don't. I will say, in terms of this setup, when it is explained to us what a probability is, this conditional setup, a lot of Bayesians don't even use a probability distribution on the margin. They'll use something that's called an improper distribution, which is not a distribution. So I tend to think Bayesians use Bayes' rule is a constructionalist operating system. So they construct this thing and they use this mathematical form, and then at the end of the day they call something a probability. When theta is not compact, i.e. it's on an infinite space, usually The reference or objective analysis and the objectivity criterion I usually pick subjectively. So again, this is just a word game. Usually this margin is not a real probability distribution. So Bayesians are often using that framework, but doing it in terms of a limiting sense and not working with probability distributions in the limit. We'll talk a little bit about that in this class. We're not going to go too far into it, but I do have a fall class where I go into much more detail about this. It's called Bayesian Statistics. I also talk about different types of Bayesians in that class, and I also compare to non-Bayesians. A lot of you have turned in your definitions. Thank you for doing that. If those of you that could on Wednesday print them out for me, that saves me some time. You can still turn them in to me. I'll show you my definitions on Wednesday. So I sat down over the weekend. I carved out new definitions for myself. I compared them to my definitions that I wrote last year, and I defined them a little bit differently this year. So, and I thought, oh, this is a good point I made last year. So I'm always evolving my definitions. And that's what I hope you'll do as well. So we're having all these conversations so that when we get into the technicalities, we know what we're talking about and we're not just doing theory, we have context for our problem. Okay, so all very fun. Saying that, it's totally reasonable for you guys to go back and forth, equivocate, reform your opinions, debate over what was meant, what do you mean by it. People have argued about this stuff for hundreds of years. This is not new. And for you guys to not argue would be kind of a disgrace to our founding fathers, so in our field. So we better argue about some stuff every once in a while. Let's just try to demonstrate also what we mean. So show what's happening. It could be that other people will do exactly the same thing that you're doing, but call it something different. And you'll argue about that. It's kind of a waste of time. But it's fun for a while. So when I was in graduate school, I loved it. You know, the debate game, let's do it. So nowadays I'm busy. So I don't necessarily want to do this all the time. Okay, this will not be our only controversy in this class. We'll see several of them, and I'll tell you, just form your own opinions. You'll hear people argue about this, but here are the two arguments. And if you guys want to discuss it in review session after class, I'm always up for it. So I usually try to just explain what the different people think, and I'll even tell you what I think, why I think it's reasonable, but I'm not going to give it to you as dogma. This is the way it is, and that's the unequivocal way to think about it. And if you think about it differently, then you can't be confident. I don't have those sort of opinions, but Eris does. That's okay. He's allowed. Okay, I want to get into the Bootstrap, and I'm going to demo some stuff for you. So I've written some code. And I want to just point out this function real quick, what I'm sampling from. So this first part of the code is really just sampling data. And it's sampling from a function that looks like this. So the way I created this function right here is I superimposed three normal distributions. So this is coming from a mixture model. And I did this just to make the underlying distribution something complicated, something that you can't easily think about. And you wouldn't know how to do mathematics on a problem like this per se. You might. But what I did is I just created three normal distributions. So that tail goes all the way out here, places most of its mass around this point. I think for my code, I made this -10. I made this 10, but I think I made this 3. So I just have three normal distributions that I'm sampling from, and I've explicitly written those down. So rand n is a normal random variable. It's normal 0, 1. When I add a number to it, then I'm shifting the distribution. And I'm shifting it to where those mu's are, right there. All the variances here are 1. I also put some heights on this. So I have some probabilities on being in each one of these components. So this is with probability 1/2. This is with probability 1/3. And this is with probability 1/6. So the formal way to write down this mixture model would be to write this down. F of x, given whatever my theta is, and my theta in this problem is going to be this collection of mu's. Those would be the things maybe I want to estimate if I knew the asymptotic form of everything. So this might be mu1, mu2, mu3. So when I write down theta in this class, I could very well be thinking of a collection of things. They're the parameters that drive the problem. You might be thinking, in a real problem, I wouldn't even know what the variances are. And so those might be parameters in your thing. You might not even know how many components are here. That might be a parameter that you have to estimate as well. And we will do that in this class. We'll see a couple approaches for working with mixture distributions. So my brief lecture on this is just to write down what a mixture looks like, a mixture of normal distributions. So this is a finite mixture model, and it looks like this. I'll say K, goes from 1 to 3. So this is our number of components. Usually I call this something like cap K. So the number of components. And I have a lot of language that I use for this, depending on who I'm talking to. So I'll switch my language depending on who I'm speaking to. And in this class, I'd like you to build your glossary up so that you're nimble when you're talking to different groups. So I might say it to you as a machine learner sometimes. I might say it like I say it as a statistician. And I might say it some other way sometimes. I might say it to you more informally in terms of English. But anyway, we need to be nimble in our the way we use language. If we need to write something down mathematically, that's because we're confused. And that's okay. We're always confused. I say, write it on the board so I know what you're talking about. Okay, so this is going to be, I'll say, pi k. You can put this in a different color. Pi k. F x, and I'm going to write down mu k. The variances are 1 right here. So this thing right here, when k is equal to 1, I mean this normal distribution. When k is equal to 2, I mean that normal distribution. When k is equal to 3, I mean this other normal distribution right over here. You can kind of see the mixture weights right here. So I'll call these maybe mixture weights. So my added bonus in this class is that we'll play around with models like this periodically. They're not in your book, so I'll introduce them to you and give you some assignments. If you can play around with distributions like this, you can do a lot of stuff. You can model some pretty wiggly behavior. So oftentimes, this is a parameter, you need to estimate it. Oftentimes, the variances in my normal model are also a parameter, and I need to estimate it. What this function looks like right here, for my problem, is they're normally distributed. Why normal? Because they're smooth and I can build a lot of functions out of it. So with mixtures of normals, I can almost represent anything so long as it's relatively smooth. So, and there's a theorem that does something like that. Fourier Series are the same as well. If something is smooth, I can model things using sines and cosines. So sines and cosines would be my basis function. And in my mixture setup, this would be my basis function. And this looks like just this, 1 over square root of 2 pi. There's going to be a sigma k in here, but I'm going to let all of those be 1 in my problem. So e to the minus 1/2 x minus mu k squared, and then I've got my sigma k squared over here, but this is also 1. So typically in a real problem, you need to estimate how many mixture components you have. A Bayesian would put a prior on that. They might use a non-parametric prior or a semi-parametric prior. They might use a parametric prior. All depends on what the fashion of now is. So the fashion of now is to use probably a Dirichlet process to model this. We will not be getting into that in this class, but it's just stuff that you might want to be aware of. Any of these things you ever want to discuss, office hours is a good time for it. Over at my office after class is a good time for it. When you see me walking around the grocery store, it's a good time for it. So we can always discuss things that I'm not going to explicitly do in this class, but I think about 15 years ago, people got really interested in estimating what the number of components were and didn't want to constrain it too hard using some parametric assumption. Kudos to them, it works well. Very computational, but we've got the resources. Okay, So my mixture model is this. These pi k's right here, I'll just say pi 1 in my problem is 1/2, pi 2 is equal to 1/3, and pi 3 is equal to 1/6. So what I would do to sample from this is I would flip a 3-sided coin with those 3 probabilities. If it lands on side 1, I'm going to draw from a normal distribution centered at mu1. And in our case, that's -10. So I'm going to flip the coin again. If it lands on the 3rd side, then I'm going to sample from this component right here. And so I'm doing a hierarchical sampling. So I flip a coin, these probabilities, and then I sample from the component. And that's what my code does. So what it does is it draws a uniform. So u being equal to rand, that's a uniform random number between 0 and 1. It changes every time through this for loop. And then if I'm, depending on what the probabilities are, I'm really doing an inverse CDF sampler, but I think you get the point. So, but I'm just sampling from a 3-sided coin in those 3 statements. So what's the probability that I'm in the first component? Well, it's mixture weight 1. So u is less than mixture weight 1. So if I get a random number between 0 and 1/2, I sample from the first component. If I get a random number that's bigger than 1/2, but not as big as 5/6, then I sample from the second component. And if I get a number that's bigger than 5/6, then I sample from the 3rd component. And this is what this does. So what we're going to do is we're going to discuss the bootstrap in terms of this. What I would love to do if I were trying to learn what these parameters were is I'd love to just go out there and sample a heck of a lot of data. So saying that we're in the real world, look, okay, we're not in the real world, we're in the classroom. But if I were in the real world, I can't just have you go back out into the population and just resample things over and over again. I wish I could, but since we're not in the real world right here, I can fake it, and I can mimic it. So it's very cheap for me to go out and sample n random numbers from this distribution. We can play around with what n is. So our techniques will be worse when n is small. Our techniques will be better when n is bigger. And if it weren't that way, that'd be a very bizarre world. So, okay. Our goal is going to be to learn something. So, what I can do is I can take my data and I can plug it into this function right here. So my data is just going to be a collection of these data points, x1 to xn. And so what I really want to estimate is this function when n goes off to infinity. So as n goes off to infinity, this will converge to the true function. So if n is anything less than infinity, this will be an approximation of that true function. And as statisticians, we want to quantify our uncertainty about this. How good is this when n is small compared to when n is big? That's what statisticians are always trying to quantify. We become more uncertain about our real quantities when n is really small, and the function is very wiggly. Okay, so just as some examples, maybe tx is the mean. So what I really want to know is the true mean, and all I can do is plug in my data into some function and compute it. So the mean would just be this. Sum I goes from 1 to n, xi over n. So we usually call this x bar, and sometimes I put an n there to let you know it's a function of a sample size. But that's x bar. If I wanted to know the variance, I could just compute it. So I could end up computing xi's minus x bar n squared, and I can divide this by n. Some people might be inclined to divide by n minus 1. That's totally fine if you like that. So maybe minus 1, maybe minus 20. So there would be no good reason to subtract 20. Saying that is n goes off to infinity. If n is really big, we're equivalent. So if you'd like to write down minus 1 right here, good. So I usually don't do it. I usually divide by n. So somebody just tell me, so that I can understand a little bit about what you understand. Why do some people divide by n minus 1?
One is that when you take the expected value, you get an unbiased estimator.
That's it. So people love this minus 1 because it makes this an unbiased estimator of true sigma. So this might be approximately, well, I'll say this is equal to some sigma. It's going to be the global variance of this thing that we're estimating. So this is sigma squared, and this is, or I should say, this is sigma hat squared, which is approximately the true value, sigma squared. So this is the truth. And we can estimate the truth using this statistic. And most of you have seen that. Somebody tell me why some people divide by n here and not n minus 1. Ankur, again?
Well, at least for a normal distribution, it's that maximum likelihood estimator.
Yeah, it is the maximum likelihood estimator. So Ankur's employed a technique and said, I know a technique, and it's the MLE. It turns out the maximum likelihood estimator is divided by n. So that's a procedure. So you've given us an algo in some sense. What property does that procedure have?
I think n goes to the infinity, it will be the same.
Yeah, as n goes to infinity, who cares, right? So even if n was 31, I don't care anymore. If it made a big difference, we got bigger problems. So, but what property do I have? So that's true. So equivalent, they're about the same. But what mathematical property? Ankur said, if we divide by n minus 1, the expected value is sigma squared. So it turns out if I divide by n minus 1, so for division by n minus 1, we have this expectation of sigma hat squared is equal to sigma hat squared. Sorry, no hat. Sigma squared. This is the truth. So on average, it's the true thing. Saying that, for any given data set, it's probably not sigma squared. It's just that we think mathematically on average it would be sigma squared. So that means that if I divide by anything else, I'm biased. So I will tell you this, that if I was interested in sigma, and I took the square root of this, I introduced bias. So it's only unbiased in one functional form. If I take a function of it, it might be biased. So it's only unbiased when I'm estimating sigma squared, but if you use this and you estimate sigma, you've got some bias. And we'll see that in the next homework problem. So you'll be able to prove that to yourself. So kind of funny, but I think it's like, it gives us comfort. It's unbiased, that sounds good, but it's only unbiased in this functional form. So if I take a function of this thing right here, I'm going to probably have some bias. How do I know? Jensen's inequality, something like that. So if I were to take the square root, I could prove things using Jensen's inequality because it's a monotone function. Or sorry, it's not monotone, it's convex. So that's what I'm going to say. So if you need a discussion of that, I think I do discuss that in this class. So in terms of the homework problem that you'll see next time. So back to my question, why do I divide by n? And wow, I just went over our time, didn't I? Still a good discussion. Turns out it's lowest MSE, mean squared error. So it brings down the mean squared error. What I'm going to do next time is I'm going to run this simulation for us. But what I'm going to do is I'm going to compare the Bootstrap that I haven't told you about, but I'll tell you what it is in a nutshell real quick. When you have your data set, what you do is you resample from it, and you sample with replacement. So you do simple random sampling out of your original data set, and you recompute the statistic. And you do that over and over and over again, and you build up a distribution of this statistic. I'll write this down formally next time. What I'm going to do is I'm going to compare this idealistic framework for you to the Bootstrap. So my idealistic framework is I'm going to resample from the population over and over and over again. And then I'm going to compare it to one data set where I resample from that data set over and over again. And I'm going to compare my inferences. And I'll put this code up online for you. You can play around with it before the next class. But this is what you're going to see when you run this. So So what I'm doing here is I'm going back out into the population and I'm resampling over and over and over again. I don't get to see this trimodal function, but I get to see data points. I guess my 1/6 probability is the middle thing, and I wrote it down slightly different. So what I'm doing is I'm just showing you this thing that I would love to tell scientists, go out there and resample over and over again. And compute your statistic over and over again. And that's what we're going to see on the left-hand side. So this is the distribution of whatever this statistic is if I go back out into the population and I resample n data points over and over again. And this is my distribution of whatever statistic I'm computing. We'll discuss in terms of the code different statistics. So the procedure will work differently depending on which stat we look at. This is the Bootstrap replicated thing. So what I've done in my code is I've taken my very last data set, one that looks like this. Specifically, it's this data set. The last one I've sampled, and I've done Bootstrap sampling. I've resampled from this distribution over and over again, not the original, the true population, and I computed my test statistic for each Bootstrap replicate. And those distributions look a little bit different. So you can look at the ranges, but they're about centered in the same place. They're a little bit different from each other, but they're pretty similar. And what I've also done is I've compared those distributions to each other using a tool called a QQ plot. So I've compared the quantiles from this distribution to each other. So I've compared all their quantiles and I plotted them next to each other. If you don't know what a QQ plot is, please look it up before next time. It's one of my top 2 favorite graphs. So it's one of my 2 favorite things to look at, QQ plots. But basically it's a way of checking to see if distributions are the same. And when this pattern is linear, then we think that distributions are the same. They're not exactly the same, they're a little bit off in the tails. So let's come back next time, run this code, discuss it, see how well the Bootstrap works, and then I'm going to move on to something different. I'm going to move on to the delta method. We're going to need to know about moment-generating functions to do that. Sorry for going over. That's it for now. I'll take questions in a moment. Thanks again, you guys. Jess.
What's the other one? Like you have 2 series, each plot is one, what is the other one?
The quantiles?
Yeah.
So I plotted the empirical quantiles for most distributions. So the QQ plot, if I just type in QQ, usually it'll compare to a theoretical normal distribution. You can compare anything to anything. I'm comparing 2 empirical distributions. So I'm comparing those 2 things to each other in my QQ. So I'm not comparing to a normal. I'm comparing to each other. So these are perfectly flexible plots, and you can tailor them to your situation. Look through the code, I'll post it for you. You'll get a handle on it. If that's not clear, I'll be running it and walking through every step and stuff. Hey, and thanks for making it, guys. We're on a roll. Okay, sounds good. Yeah,